Poke. There we go. Describe the end behavior. You will describe the end behavior in our pseudo limit notation. Not that up and down BS. And intervals of increase and decrease. We talked about that. It was one of our later examples. Along what x's is this function going up or down in terms of y's? So along what x's is it doing that stuff? More than sufficient time. Before I go doing anything, end behavior based on leading term. It's a negative x to the odd. So what do I know it has to do? As x goes all the way back to negative infinity, and as x goes all the way to infinity, it's a negative odd. You even got a chart for it, right? Goes to positive infinity and negative infinity, respectively. Okay, I know that. I got a chart that tells me it. Next, I could just look at the graph. And as my x's go all the way back to the left, well, it's going up to positive infinity. As my x's go all the way to the right, they're head down to negative infinity. So that's another way to tell. Now, it does say to estimate. If you found the actual values of those extrema, said we kind of talked about it, it's not official yet. That's why I have estimate on there. If I do, I'm going to turn my grid line on just so it makes it a little bit easier to estimate that. I would say that this point and this point, if I ballparked them somewhere around negative 1/2, negative 2.5, or negative 5/2, if I ballparked it around 1/2, 1/2, just so long as whatever you estimated it as wasn't a whole number and it was a fraction that made, or a decimal or fraction that made kind of sense, right? Like if on this one you said about 3/4, 1/4, like I'd say that's more reasonable than a 1/2. Get what I'm saying? Like everyone was estimating, people are going to have different answers. Now that's if you're going to guesstimate. Remember, you can find these correctly. If you calculate a maximum somewhere between 0 and 2, it'll just straight up tell you what that point is. Okay, so if you use that instead, great. Yay, awesome, good for you. I'm saying you didn't have to. So if I'm going to estimate my intervals of increase and decrease, you're asking, as you go left to right across the graph, is it headed up or down? So as I go left to right this way, my graph is headed down and down again. And in between there, it is headed up. So you're stating on what intervals are your y's increasing or decreasing. So I would say it is increasing from here to here. Along what x's is that? So whatever numbers you had on your coordinates here, I would say about negative 1/2 to 1/2 if I'm estimating. Now, if you used negative 2/3 to positive 3/4, like, are we cool? I don't have to keep beating that to death. My numbers here are not going to be the same as your numbers. Versus decrease is going to be in two locations. It's going to be from negative infinity to whatever the x value was that you estimated it as, and again from 1/2 onward. Now I use the big U with a little more junk in the trunk. It's the union symbol. If you remember doing like Venn diagrams and stuff, the difference between and or, union and intersection. Maybe you did a little bit more of it in biology. I hope you're using set theory in biology. Maybe. Okay. But again, your numbers here are going to be different than mine. I was just ballparking it. But the important part is that you're using the x values, not the y values. When I state intervals increase and decrease, I'm stating along what x's are my y's going up or down. Okay? So, did you have to infinity to negative infinity, my increase, my decrease, and I'm going to use one floating for you got your notation right. Your notation is correct because how we write it matters.
So did you just include it in notation, or is it all right if you just wrote it?
If you just wrote and or also comma, I'm okay with it. Yep. You don't have to use that symbol specifically. Yeah, you want to use the caret for and, that's cool too. When I say the notation, I mean like over here you actually use this notation instead of up and down. You actually put an interval. You have parenthesis, number, comma, number, parenthesis. You have two different things. You labeled that they were increase and decrease. That's what I mean. Okay. Any questions on var? Okay. Then, shoop, you go away. You get small. You go away. I'm not even logged in yet. Yet again, I got a person asking questions. Really good ones, too. Hell of a conversation. But, you got anything for me? Which asks what?
It asks for the terms decreasing.
Okay. I really don't want to poke the thing because Clever takes forever to log in on this. There we go. Leave. Go away. Refresh. I mean, a single sign-in is great, but the interface between Clever and Pearson is not the greatest. Because Pearson is not the greatest. Okay. Others besides the 33s? Anything? Okay. Then graphing them seems to be okay. The part we left off at was a little bit about this multiplication business. Now, if I remember right, we started in here, probably got A and B done, not to C. Okay. So round one, I've got x plus 2, x minus 2, x minus 3 is x squared minus 4 times x minus 3 is x to the third minus 3x squared minus 4x plus 12. Okay, that one's going to have zeros at negative 2, positive 2, positive 3. And I'm not sure about the extrema on it, but I know it's going to... Oh. Something like that. I don't know how far up or down it's going to go. I know it will hit the point 12, though. Part A, how do I know that that hits 0, 12? Right? If I jam a 0 in for x, you get 0, 0, 0, 12. Right? So function of 0 is 12. So I know that's my y-intercept. It's probably not my maximum, but I know it at least hits that point. That's where you use your calculator to find the ballpark, what those look like. What I want you to pay attention to here, common theme. Since these two zeros are further apart than these two, that usually means that the distance of the extreme in between them is going to be much bigger. It's kind of like, you ever played with, maybe in physical science or middle school or whatever, one of those little sliders that has the magnifying glasses on it? You're playing with like the reflection of the candle in it, or anyone? No? Yeah. One person? Yeah. As you change the distance between things, it affects what's in between them. These are further apart, so they're going to have a higher extreme than these that are closer together, so their extreme will be a little bit smaller. It's just a general behavior thing. Part B. I'm getting fuzzy memories now. I think this is where we left off. We have x plus 2, x plus 2, x minus 2, x minus 3. And we had said the best way to probably go about that is to multiply 2 together, and then multiply those together. That's right, because we were going through different ways to multiply them, where you can stack them and multiply them old school, like 3-digit numbers. You can distribute and just have a bunch of junk and then find your like terms. You could start to organize them by like terms as you're distributing. And I even showed you where you could do it almost like a big honkin' Punnett square. And there's some kids who are going to like every one of those. I don't care how you do it. You just multiply the way that works for you. If I take x squared times this stuff, I will get x to the fourth minus 5x to the third plus 6x squared. If I take 4x times that stuff, I've got 4x to the third minus 20x squared plus 24x. If I take 4 times that stuff, I get 4x squared minus 20x plus 24. And the reason that I write them staggered like that is it's almost like our old 0 as a placeholder thing when we were multiplying? Remember longhand multiplication. If I use that 0 as a placeholder, it forces all of my like terms to be in columns. Some of you liked this. Instead, and then if you do it that way, all of your like terms will be on the diagonals. Okay, they're just methods of organization. The way that you organize things doesn't need to be the way that I do, doesn't need to be the way that the person next to you does. For example, in here, I print out the notes. I do that because over the years when I just had it available to kids, A, more and more kids started using them. B, kids couldn't follow basic printing instructions. And you'd have kids show, you think this packet is thick, wait until you get the kid who comes in printing 1 slide per piece of paper because they can't figure out how to work the settings. Okay? Literally 4 times thicker. But also because the way you organize things is different. Have you looked at your notes compared to someone else's notes in, I don't know, history? Maybe this person uses actual concept maps. This person just writes down 5 words and then sleeps. Maybe this person puts a paragraph. Maybe this person meticulously writes everything that's on the board and doesn't even know what they wrote because they're just struggling to keep up. Okay? Your method of organization is going to be different. The method of organization for multiplying can be different so long as you get to, at the end of the road, you all have the same thing. You should have f of x is x to the 4th minus x to the 3rd minus, what's that, 8? 10? 10. X squared plus 4x plus 24. Okay? I'm pretty sure that's where we left off. So you notice this one has the exact same zeros. It has -2, +2, +3. See the leading term? Positive x to the even. So where does it start? As I go all the way to -infinity, where does it start? Positive infinity or negative infinity? If it's a positive even polynomial. That's right, use those notes. That's why we got them. A positive even will start up at positive infinity and it will end at positive infinity. Okay. It has a y-intercept way up at 24. How do I know that this thing is going to look like that? Okay, the end behavior tells me it's going to start there, but how do I know what it's doing at those spots? Okay. But why doesn't it go through here and then like that? All right. You start getting, let's just put them both on the same graph. Get your calculatron. Let's put them both on the same screen and see what's up. Y is, Claire, we have a x minus 2 times a x plus 2 times a, what was it, x minus 3? Yeah. For the first one. For the second one, I've got a pair of x plus 2's. Y'all okay if instead of a pair of x plus 2's, I just say squared? Okay. And then x minus 2, and then a x minus 3. Okay, so the only difference in these is literally that this has an extra x plus 2. My window, because we know that that has that y-intercept up at 24, I'm going to make this go, we'll say -5 to 30. I just want to make sure that I got enough vertical space to see what's going on. I don't even know that that's enough, but we know that we have y-intercept to 24 for one of them. So graph of a versus Why does that goes through the axis, that goes through the axis, that goes through the axis, the blue one bounces off the axis. Look at your zeros. I want you to see if you can figure out why that happens. Why do most of these go through the axis like a line, but that one bounces off the axis? Look at your zeros. Look at how many of each zero there is. Okay. Now what if I what if I change that for the purpose of this conversation to just zoom square in on the x-axis? That doesn't look good at all. Maybe we need to widen that out. Let's go from -4 to 4. There we go. It went through like a line, 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 went through like a line. What kind of graph is that? Parabola. Parabolas have a degree what? And that zero happened twice. The behavior of zeros matches what's called their multiplicity. Okay, they say, how are they different? How are they similar? Well, they got all the same zeros, but their end behavior changes because it depends on how many times a zero happens. In fact, am I kind of jumping the gun there? No. Okay, so before we do this, I'm actually going to jump ahead to this slide right here to talk about that. It's pretty simple. If I have x minus c, so whatever the zero is, just number, then n determines the behavior. For example, if I have x minus c to the first, it's going to look like a line. If I have x minus c to the second, it's going to look like a parabola, and it's going to bounce off of that zero. If I have x minus c to the third, then it's going to have a kink in it right there like a cubic. If I have x minus c to the fourth, it's going to be kind of like a parabola, but it's got a little more junk in the trunk. Okay, all about that base. Okay, it's going to be a little wider at the base of the parabola because it's not actually a parabola. Okay. However many times the zero happens determines the behavior at that zero. Another way to say this is, see how this is a line and that's a cubic, and then the next one will be a quintic, it's just sharper. They all start at one end and go to the other. So they will always go through the x-axis. Whereas evens, they always start in one place and end in that same place. So they will always bounce off the x-axis. Okay. Odds go through, evens bounce off. Because at every one of those zeros, however many times the zero happened, that changes its behavior there. Okay, think about the first time that you went over to so-and-so's house. You're probably on a little bit better behavior the first time, weren't you? A little more respectful, a little more willing to say please and thank you, making sure you take your shoes off, all that kind of business. If you've been over to that person's house 40 times by now, aren't you almost treating it like your own house? Like, I just live here. Maybe their parents even say, she just lives here. Okay? The number of times that you are at that location changes your behavior at that location. Same thing happens with polynomials. Those are called a multiplicity. I also want you to know that the way the book wants us to write this is, like for this guy up here, they would say that x is positive 2, positive 3, remember set them equal to 0, negative 2, and the book says multiplicity 2. Mathematicians are notoriously lazy and don't like writing things. So this isn't in any book I've ever seen. This is my notation. You don't have to, but it just seems natural for kids who, like take high school science classes to just put a subscript on there to say there's two of them, like H2O. There's two hydrogens. Okay. So if you're solving them and writing out their zeros, that's how the book wants you to write it. I'm okay with you writing it like this. Multiplicity determines behavior. Nice and simple. Cool? So, back here, we need to get our multiply on. Write a quadratic that has just these two zeros. Write a cubic that has those three zeros. Sketch graphs of both. They don't have to be perfect. They have to have the right end behavior and zeros. And while we're at it, probably the y-intercept because it's easy to find. Should do the attendance thing. Got everyone else, right? Yeah, we do.
Just put that in the calculator.
Remember, the directions do say what is a quadratic and a cubic. Yes, you can graph by just writing the factored form, but you have to write what the function is. You gotta do both. Doesn't. Both have the same zeros. Contestant 1, just a straight up quadratic. The switch with contestant 2 says, now it's going to have another one of these. Which changes up how my graph looks. Okay. Changes it quite a bit. I've got a y-intercept of 27. I've got zeros at 3 and -3. But what might help me to graph this is if I write it like this, it reminds me what my behavior is going to be at each of them. This happened one time. So at -3, it's going to go through it like a line. This happened 2 times. So at +3, it's going to act like a parabola. My leading term tells me it's going to start at -infinity, do stuff, and go to +infinity. So I smash those 3 ideas together to say it's going to come up through here. I don't know how far. And then bounce off of this one and head up. Now, if I hit 9, and 9 is times 3 is 27, I can change the scale on the graph. Now, I don't know exactly where the maximum of that is. I'm assuming that is the maximum because it's equidistant between the zeros. I'm assuming that. I'm probably wrong. But I did just say sketch the graphs. As long as you have this, the y-intercept, the zeros, the correct behavior, I'm cool with it for now. Okay? But you notice at this 0 it goes through, at this 0 it bounces off like a parabola. Okay? The multiplicity of the zeros determines its behavior. So, when they ask what are the zeros of the thing and what are the multiplicities, you better get your graph on. Maybe your factor on. Could I factor that? Yeah, GCF, right? So if I have x to the 4th minus 2x to the 3rd minus 8x squared, what's the greatest common factor? Leaving x squared minus 2x minus 8. How does that factor? Come on now. Factors of -8 that add up to -2. There we go. Man. Our brains still in sugar crash mode?
Yes.
See, your generation actually gets it pretty good for Halloween because you get my generation who grew up getting stiffed with itty bitty little tiny things and like Jolly Ranchers and Smarties saying screw that and handing out full size candy bars to kids. Like down with the system. At least that's what we do. We go to Sam's Club and we buy like a case, several cases of full size actual convenience store candy bars. Just like, here you go, kid. Nah, because right when most people are trick-or-treating is bath and bedtime. But we're on toddler time in this house. I see x equals 0. It happens twice. 4 happens once, and -2 happens once. So if I'm going to graphify, whoa, there we go. That's better. It's going to bounce off of 0. It's going to hit 4 and go through. It's going to hit -2 and go through. What else could I say about, do I know my y-intercept? How do you find the y-intercept? Figure it out.
Put it in the calculator.
Y'all, don't just wait for Jaden to figure it out.
I'm figuring it out.
What does y-intercept mean? It crosses the y-axis. When it crosses the y-axis, x is 0. How do I find a y-intercept?
Y-intercept is 0.
Plug a 0 in for x. If I plug a 0 in for x, what do I get for y? It's almost like we already have it because it hit y equals 0. Y'all, I'm supposed to be the sleep-deprived one. What's going on here? Y'all killing me. All right. What about end behavior? Okay. Positive, even.
Negative infinity to infinity.
We just need to like go run laps or something. Wake up.
Yes. We do actually.
Wow. Okay. A positive even. Y'all go look it up. What does a positive even do?
Dude, breakfast gets done at
Okay. It's a positive even. So it starts up here at positive infinity. It will come do things and then go back to positive infinity. It goes through negative 2. It goes through 4. It bounces off 0. So start at positive infinity. Come through negative 2. I don't know how far. Bounces off of 0. I don't know how far. Comes back up through 4. I hope you don't put that on your paper and pen. Because if I'm going to graph this for real, I need to know how low does it go. Go grab your calculator and let's find those actual points. Find out how far does this thing go. So y is clear. Clear. So we had x to the 4th minus 2x squared, or no, cubed, right? Cubed minus 8x squared. Okay. Now when you're finding these minimums, we're going to talk about them later. One is called a relative, one is called an absolute. If I want to find a minimum here, then put blinky on either side of here. I can't say my left boundary is here and my right boundary is here and it give me both of them. It's not going to do that. It's just going to give me whichever one's closer to my boundaries. You just have to do this twice. I'm going to calculate a minimum somewhere between negative 3 and 0. Oh. Okay. So I wasn't too far off. At negative 1.3 something, negative 6.3 something. And if I'm going to put this very specific point on here, I'm going to label it approximately Negative 1.387. Mine's really blurry. Isn't that an 8 next to it? Or is it a 0? Oh. And negative 6.353? Or are you going to tell me that's a 1 and not a 7? Okay. So I've got that point. Go find the other one. Calculate a 0. No. Calculate a minimum. Somewhere between, I don't know, 0 and 5. As long as it's in there, we're good. How low does it go? Holy. Okay. Yeah, we weren't going to get that by just winging it, right? We weren't going to get that by just winging it. So I'm going to put a point at approximately 2.886, negative 45.335. Now, if I'm going to do that, to make my graph, I probably should change my scale. Okay. If I want to go down to negative 45, here, how much room do we got? There we go. You got enough room, like you could go by 2s, right? Okay, so you got enough room to go by 2s, and then you just connect your dots, right? Okay. So, it's not enough to just say, I can find the zeros. I want you to find the zeros, know what the behavior is at the zeros, and then go use your calculator to find the points in between to make sure that you're more accurate. So same thing for down here. That's a pixelation error. Okay, start by factoring. Wherever the zeros are, mark those. Note next to them what's their multiplicity, how does that change its behavior. Use the end behavior to say where it's going to start and finish on the graph. Then use your calculatron and go find those extrema in between them. Find out just how far up or down this thing heads.
In order to get a positive one, negative, so you set zero, so x equals so this 0 minus 0 and positive 2. What? You have to set x equals 0. No.
Yeah, but your teacher's 0.
I do think it's
Start with factor stuff. Note next to them what your behavior is going to look like. The first zero occurs one time. So it's going to go through like a degree 1 or a line. The second zero occurs twice. So it's going to bounce off of the axis like a parabola at that point. Look at your leading coefficient. Positive x to the third. So my end behavior is already known. I'm going to have a 0 right here. I'm going to have a 0 right here. I know it's going to start down at negative infinity, do stuff, and go to positive infinity. Okay. Now it's just a matter of in between, what does it do? Like, I know this thing comes down here. I know it comes up there, bounces off, goes up there. I'm not sure exactly where. So that's where my calculator comes in. Okay, I've got that general behavior. Go to my calculatron. Y is clear. X to the third minus 4x squared plus 4x. Graph of oh, not very high. I calculate. My looks like a maximum somewhere between 0 and 1. Okay. Now I know that's 2/3, so I'm going to write that part. But the y part of the coordinate, it's an irrational number. Oh wait, that's not an irrational number. No, you don't just close enough it. Point 185, 185, 185, 185, 185, 185, 185. There's a 1 and 185 over 999 as a fraction. Or if you don't know what it is, you can always come back here and say 1.185, 185, 185, 185, 185. Just keep doing that and say, math, change that to a fraction for me, please. Ba-doop, boop. So it turns out I can actually write exactly where that is. I can say that at 2/3, 32/7, 20/7. Good thing I didn't write it yet.
Can't even see because you covered.
Yeah. I am the anti-adult in the room. Do as I do, not as I say. Wait. Maybe. Oh. So, come up from down. Ooh. How far out should I go?
Not far.
Maybe I could go to my table and find out a couple other points. -1, -9, 3, 3, 4, 16. So at -1, -9, 3, 3, 4, 16. Now I have more than enough to sketch the behavior of my graph. Okay, so it's kind of a combination of multiple skills where I can factor to find zeros and behavior. I can look at the equation itself to find behavior. I need my calculator to calculate my maximum, and then I also use my table to get some more points to fill it out. Yup. I want you to write it down because it's important. If you are going to graph a polynomial, those are your 4 steps. Polynomials are going to start getting weird. So far, we've been doing cubics, maybe a couple of quartics. What happens when I toss a quintic at you that has only 3 real zeros and 2 imaginary? If you want to graph it for real, not just wing it, not just sketch what you saw on your calculator screen, there's your 4 steps. You need to graph and label your x and y intercepts. You need to graph and label your extrema. Extrema are your minimums and maximums. Okay? I'm very fuzzy remembering that this book did that kind of out of order. I think extrema is a whole other section. So we're just kind of ahead of the game there. It'll make us go through that stuff fast. And then a few other points, meaning before you go connecting the dots, before you go winging it on the outside of those zeros, just go look at your table, see if there's a couple of nice points. If there are, use them. If there aren't, then wing it. But if there's a couple nice points, use them. Womp. So, can you or can't you? Show me thumbs. If I gave you any of these are just quadratics. That's dumb. If I, ooh, we need to practice that. We're going to extra practice that. Create a polynomial that has these zeros. You get to go distribution bonkers on it. Yeah, and now multiply it. No, these started with the polynomial and you factored. This is starting with the factors, you make the polynomial. We have to be able to go back and forth between different representations. Different representations have different features. I'm leaving mine kind of different colors like that, so you see I multiplied the first two together, I multiplied the second two together. But now I need to multiply those two quadratics together. So if I take x squared times all that stuff, x to the fourth, 3x to the third, minus 4x squared. I'm just distributing. X squared times x squared. X squared times 3x. X squared times negative 4. If I take negative x times that stuff, it's negative x to the third, negative 3x squared, positive 4x. If I take negative 6 times that stuff, negative 6x squared minus 18x plus 24. You see how I left all of my stuff kind of lined up in columns? I do that because it's a method of organization. This is one way to organize. I don't have to organize it like this. That's just one way. Minus 7 minus 13. Okay. This is a way to organize. Now, if I'm remembering correctly, last week when we had started talking about this, there were several of you who kind of perked up at the idea of doing this by box method. So I'm just do again. See if some of you like that or not. If I write this as x minus 3, x plus 2, x minus 1, x plus 4, a different way to organize it is, got a lot of sophomores in here. Have you gotten to Punnett squares yet? Do you at least remember them from middle school? Like the whole dominant recessive trait thing? Everyone like roll dice or flip coins for dominant and recessive and just see does your baby have one eye or five kind of thing? No?
Yeah, they gotta try.
Okay. So the way I would write this is an x and a minus 3, an x and a positive 2. That's this. And I'd fill it in. I'd say that's x squared. Negative 3 and x is negative 3x. X and 2 is plus 2x. Negative 3 and 2 is negative 6. Look at your diagonals. Those are your like terms. And you get x squared minus x minus 6, which is exactly what we had before. If I instead do this, I have an x and a negative 1, an x and a positive 4. X times x is x squared. X times negative 1 is negative 1x. X times 4 is plus 4x. Negative 1 by 4 is negative 4. Again, combine your like terms and get x squared plus 3x minus 4, same as before. Some people prefer this. Some people, this is gibberish. And then smash those two together. In one big box and say I have an x, x squared, a 3x, and a negative 4. I have an x squared, a negative x, and a negative 6. And then x by x squared. 3x by x squared. Negative 4 by x squared. If you have the one that if you wrote down the one that I wrote before, you should see these same things again. It's just this is a different way to organize it. Negative x to the third, negative 3x squared, positive 4x. Negative 6x squared, negative 18x, positive 24. And then again, your like terms, your like terms, your like terms, your like terms, your like terms. Okay? Show of hands. Because it depends on the year. Honestly, it depends on your experience with biology. Maybe it's fine now because you haven't gotten to it yet. Show of hands. Box method. Who likes it? Like, that's my jam. I'm switching to that. Okay? You usually get a couple of the visual, hands-on thinkers are like, this is my thing. Why haven't I been shown this before? Y'all know you can go old school with this too. You could have x squared plus 3x minus 4. X squared, what was the other one? Minus 6 was over here.
Minus x.
You can just do this like old school multiplication. It's just each of these is its own digit. That's all it is. You still get 24, negative 18x, negative 6x squared. 0 as a placeholder. 4x, negative 3x squared, negative x to the third. Zeros as placeholders. Negative 4x squared, 3x to the third, x to the fourth. Okay? Do which way works for you. I don't care which. If I do it a different way up here than what you're doing at your paper, that's okay. But you have to be able to do this. All right. Oh, hey, we jumped the gun. There's our extrema. Okay, we know that now. Maybe let's just add in some verbiage to it. Something is a relative maximum or minimum compared to an absolute maximum or a minimum when it's only the maximum or minimum in that area. Okay? I call these relative because this is not the highest that it ever goes. It's only the highest that it ever goes in that area. Okay? So I want you to have a note for that. Something is a relative minimum or a maximum versus an absolute minimum or a maximum if it's in that area versus for the whole graph. Okay. An absolute minimum is the lowest it ever goes. Meaning its end behavior is not negative infinity. A relative minimum or maximum is just the relative height in that area. Okay. So y'all can find them on a calculator, right? Like we were just doing that. Everyone knows how to do this. Strange noises mean do it. Because if one person makes strange noises, there's at least 5 in here who have that same thing. They're just not as verbal. Find for me the extrema of this. Relative or absolute, maximums or minimums. Remember, out to the 1,000th place value. Sometimes these will surprise you and have a nice number. Most of the time they're going to be trash irrationals. Now, in the olden days, and by the olden days I mean Friday, we probably would have just looked at this graph and said, here's my zeros, and just called that negative 1, 3. It is not. And from this day forward, we will never call it that. We will always find it the real value. So we're going to say, calculate a maximum somewhere between negative 2 and 0. And I will say that there is that relative or absolute?
Relative.
So I'll say there's a relative maximum approximately negative 0.865 3.132. I'll say it's relative, not absolute, because the graph does go higher than that. I'll say it's a maximum because it's the highest point in that area. I'm also going to have another relative minimum over there at somewhere between 0 and 1, as long as it's pointing in at it, at approximately 0.642, negative 2.04, 2.004. Okay. Three places. Use the approximate symbol because we are cutting off part of the actual answer. If you ever cut off part of the answer, you have to put approximately, because you are not equal to. It is not exactly this. We were having that discussion last hour in pre-calc. What usually happens is kids will take Algebra 2 or pre-calc with me, and then they'll go and take our science classes, especially chem and physics, and they get mad at the teachers because our science teachers are prone to just using decimals and rounding in their work, and not just rounding in their work, but a certain teacher rounds in this step to use in this step, rounds that to use in this step. Like, you've all played the game Telephone, right? The whisper in the ear thing, like, funky bunnies bake brownies for Weebles. I don't know. And then goes down the chain, and by the time it gets over here, it's like, yo mama. Like, it's not even close to what was said. That's what happens mathematically when you keep rounding your answer. And our science teachers do that. So just so you know, I am going to make you get the real answer. I am going to make you put approximately when it's not the exact answer. Then you're going to go over there and they're going to tell you to do the exact opposite, and everything you'll do in those classes is wrong. So, can you do it in words? Yeah, you can do words. Okay, the design of a digital box camera maximizes volume while keeping the sum of the dimensions at 6 inches. What are dimensions? Length, width, and, in this case, length, width, and height, or length, width, depth. Okay, it's a box. Length, width, height is what most people are going to go with. And it says it maximizes the volume while keeping the dimensions. Okay, as soon as I hear that, I'm going to put volume is length times width times height, because I know that's how volume works. It also says that the sum of the dimensions is 6 inches. What can I write now? Length plus width plus height is 6. Length must be 1.5 times the height. So I can replace this with 1.5 h, which means I can simplify the whole thing down to 2.5 h plus w is 6. What should each dimension be? Well, I can also cross this one out, right, and say volume is length is now 1.5 h. So I've got 1.5 h times w times h, which is 1.5 h squared times w. I still have too many variables. I want one variable on the right side, not two. Is there any way that I could rearrange this to get rid of that w? What Jaden said, I hope that you actually finish this since we are apparently done. Okay. This and this need to be finished in your notes, but it sounds like we're done. Okay.